Okay, guys, good morning, guys. So let's continue our discussion on flip-flops. Yeah, here we go. Hold on a second. Okay, so let us start our discussion. Okay, here we go. Okay, so last class this edge triggered because it's triggered when I was particular is that of course it's specified in the syllabus one thing. In this we are discussing edge triggered only for the D flip flop. Okay, why it's only D? Why not JK flip flop or why not it is RS flip flop? The reason for that is basically all are same. The basic circuit components are same. The only difference comes in terms of how the input is applied. Whether it is applied commonly, then it's a T flip flop. With a complement, it becomes a D flip flop. Okay, so that there exists a basic difference. And between the latch and the flip flop, latches are asynchronous, no clock pulse. Flip flops, they are synchronous because it is applied with the clock pulse. So with the intention of synchronizing multiple stages of flip flops. Okay, here we go. So, okay, let us continue. People are joining. So, okay, yeah. Okay, yeah, here we go. Let's okay. Let us we'll discuss this T flip flop. Okay, sorry, D flip flop. Okay, yes, the basic idea here is very simple. That is, if you observe this, um, you know, it's triggered a D flip flop. Basically, it is a D type of flip flop. It's triggered. Somebody's on the line. Okay, so it's triggered D flip flop. What we hold on a second. Okay, what we notice is that basically, see, this is a basic structure of what is known as a flip flop. It's not a flip flop actually; it is a latch. Basically, it's a latch. Like this, it's a basically it's a SR latch. If you can know as we saw last class, basically it has a input called as S and R. Okay, it is SR latch. Similarly, we find similar latch circuit at this stage. Okay, it has two inputs, one from the output of the NAND gate 4, NAND gate 4, another is the clock pulse. No, not the, yes, another is the clock pulse, correct. Another is the clock pulse. This is also another D latch. Actually, SR latch, actually, of course. We can call it D latch because anyway, we are implementing flip flop using latches anyway. Okay. Hold on. Okay. So SR, okay. SR latch. Here there's one more SR latch. Okay. The inputs for this SR latch is one is the S input and the other is the clock pulse. Another is the output of the feedback. Basically, it's a feed forward connection. Output from the the NAND gate number 4. Hold on a second, I'll erase all this so that. So, okay. So there are basically, if we take this, somebody's on the line again. Okay. Okay. Yes, here we go. Okay. So there's one more latch here, SR latch. This SR latch also has input. This we discussed actually. This end, this is a D input. Other input is nothing but the R input. Okay. Fine. Just now for a SR latch, if you see the SR latch, truth table or characteristics table. Okay. What we find is when both the inputs are 1 1. Okay, it is no change in case of a SR latch constructed using the NAND gate. Okay, okay, yeah, here we go. So SR latch, when both inputs are 1 1, since it is made of NAND gate, output does not change. So output retains its previous value. Okay, output Q and Q dash. Our intention here is to make the circuit, this D latch, sensitive only for the edge of a flip-flop. Okay, either rising edge or a falling edge. As we understood in the last class, that based on whether it is a negative pulse or a positive pulse, we'll have you know rising edge first or falling edge first. So that is the basic difference what we'll get in the. Yes, here we go. Okay. So for a positive, this is a positive pulse. In a positive pulse, the rising edge comes first. Okay, this is a rising edge. This is a falling edge. In a negative pulse, what happens is that the falling edge comes first, falling edge, and then comes the rising edge. Okay, fine. Here we go. So based on this difference, we can have a slight change in the operation of the circuit. Otherwise, ultimate intention is to make the flip-flop edge sensitive. Okay, it should change only on the transition of a clock pulse, not during its no, constant state. That is either during on state or the off state. Okay, how to do this? So for this, what we have to do is we have to make sure that this S and R should be at logic 1, because when both are 1 1, output does not change. No change in the output. So output not to have a change when the input changes. Okay, input changes means for a duration, for a particular duration, input should not change. For that duration, to have a no change in the output, S and R should be constant. Okay, yes, this one concept. The other point here is I'll check whether the clock pulse is. Yes, wait. I'll come back to that point. First, I'll discuss this clock pulse. So this is very slow. Okay, here it is. Clock pulse. Clock pulse. Is just a second. We had a clock pulse, no? That the clock pulse. Okay, not in this material. Yeah, here it is. Okay. Okay. Yes. Okay. Just now observe this. We know that when we apply the data to flip flop, okay, sorry, to gates, okay, we are applying a square pulse. It's nothing but input logic, digital data, 0 to 1. But what happens is that this is ideally this should have been the case, but practically this is not the case. Practically, this is what the kind of waveform we get. Okay, when we see this kind of waveform, what we understand here is There is what is known as a rise time. This we had discussed in the class also. Okay, physical class. So rise time means the when the clock pulse goes from 10% to 90%, that time taken by the clock pulse to go from 10% of its maximum value to 90% of its maximum value is called as a rise time. And the fall time is when it goes from 90% of its maximum value to 10% of its maximum value. We call it as a fall time. So this is also called as a hold time and what is known as high time as well as low time. Okay, that means when the clock pulse is applied, the logic gates take some time to read the data. For example, let us say one input is a clock pulse, another input is D input, for example. Okay, what happens is that when the clock pulse is applied, immediately output will not change. For output to it is going from 0 to 1. Let us say D is also 1, for example. Okay, for output Q to change to 1, it takes some time. Okay, that is called as a settling time. Basically, that we call it as a settling time. Settling time, why? Because it takes some time to for the input to settle. Once the data is settles, okay, then hold time means it remains constant. So it's steady state. Basically it's a steady state. Okay, using this concept here in this edge triggered flip flop, when the input is applied, okay, and when the clock pulses are also applied, the circuit takes some time to change the output, some delay because of the delay of the gates. Okay, so after the delay, when the input settles down, okay, when the input is steady, after that when the output takes some state, either low or high. After that, whenever the input changes during the on period or during the off period of the clock pulse, during the on period or during the off period of the clock pulse, output should not change. Why? Because we want the circuit only sensitive only to the edge of a clock pulse. Okay. So thereby, what for that? What is requirement? What is the requirement here is that S and R should be logic one, so that output does not change. Output can be either 1 or 0. No change. Basically, we should say no change. Output does not change. Okay. Yeah. Here we go. Okay. To understand this concept, so ultimate, see, this is just a SR latch. Ultimate intention is to keep S and R at the logic 1. Okay. So thereby, the four possible cases, okay, what we discussed in the last class, with clock pulse 0. Okay, with clock pulse 0 and S and R at logic 1, because ultimately we don't want output to change. Clock pulse 0 and D 0. Let us analyze the circuit now. Okay, so this input is 0, this point is 1, this point is 1, this is clock pulse is 0, S is also 1, R is 1. Okay, fine. Output of NAND gate 4 is applied as input to the first NAND gate, which is equal to 1. Okay, S is 1, so this is 1. Output of the first NAND gate is 0. When this is 0, this is made sure this is 1. No problem. Okay, fine. When D is 1, what happens when the D is 1? Okay, now observe the changes, guys. When the D is 1, though initially it is 0, when the D is 0, what should be Q? Q should be 0 because it is a D flip flop. When the D is 0, Q should be equal to 0. Okay, let us say clock pulse is still in the 0 state. Okay, clock pulse is still in the 0 state. Then D is set to 1. D is set to 1. Let us see what happens. This is 1. Okay, this is also 1 because R is should be 1, so we have to maintain R to at 1. When both inputs are 1 1, output of the NAND gate 4 is 0. When this is 0, this input becomes 0. Output of this third NAND gate is 1. Okay, fine. Here we go. Okay, now the other side, input for the first NAND gate is 0. Okay, which will force the NAND gate 1 to go to 1. Input of the second AND gate is 1, clock pulse is 0, which will ultimately force the S to be set to 1. Okay, so what we observe difference between these two circuits is that clock pulse is 0, it is still 0. S and R are equal, are both are set to 1, though, sorry, S and R, correct, sorry, not this one. S and R both are set to 1, though D changes from 0 to 1. D changes from 0 to 1. When clock pulse is still low, S and R are equal to 1. which will make sure that Q does not change. Of course, Q is actually 0, still 0. Why? Because initially it was 0, it is still 0. Generally, we can say that no change in the output. No change in the output when the level of the clock pulse is applied. Somebody is on the line. Okay, just okay. When the level of the clock pulse is applied. That's okay. That's fine. Okay. So this is for the clock pulse 0. When the clock pulse is 0. Now let us see when what happens when the clock. Okay. Guys, otherwise, what is the difference you see, guys? When D is 0, clock is 0, output of the first NAND gate is 0, and output of the fourth NAND gate is 1. Okay. Observe these two. And when the D changes to 1, D changes to 1, output of the first NAND gate is 1, output of the fourth NAND gate is 0. That means when D has changed, first gate and the last gate outputs have complemented, first gate and the last gate outputs have complemented, but S and R are still at logic 1, which will make sure that Q does not change. Q does not change. No change in Q. This is what our ultimate intention. Okay. As long as clock pulse is 0. As long as clock pulse is 0. Somebody is on the line. Okay. Yeah. Here we go. Okay. Is that okay? Yes? It's very simple. Okay. So ultimately, we have, we made sure that when the clock is 0, even though input changes, output does not change. Okay. Next case, when the clock pulse is 1, this is 1, this is 1, clock pulse is 1. Okay. When D is 0. Okay, so let us analyze the circuit. When D is 0, okay, this from where we come to this stage, from previous stage to this stage we are coming. In the previous stage, S and R are equal to 1, S and R are equal to 1. Let us see how does it changes now. Okay, as the input changes. Here we go. As the clock pulse changes. Okay, because initially, let us say both are 1 1. S and R are both are 1 1. Okay, uh, initial condition. Okay, now D is 0. This input is 0, which will force this input to be 1. This is 1. Okay, and this is also 1. Let's observe this. Initially, it was 1 1 initial condition, but because of D0, the output of the NAND gate is 1 and clock pulse is also 1. You can observe, clock pulse is also 1, which will force the output of the NAND gate 3 to go to 0. Which will force the output of NAND gate 3 to go to 0. That means R will transit from 1 to 0. R will change the state from 1 to 0. Okay, fine. Because basically it is because of the clock pulse. If clock pulse would have been 0, R would have retained at would have stayed at 1. Because clock pulse is also 1, it is changing. No problem. Okay, fine. What about the first NAND gate? First NAND gate, one of the input is 1 because there is a feedback from the output of the fourth NAND gate. This is also 1 because of the S is 1. Initially it was 1. So output of the first NAND gate is 0. This is 0. S remains at 1. No problem. S remains at 1. Okay. So this is when clock pulse is 1. That is clock pulse is I. Okay. So because D is 0, what should be Q? Q should be set to 0 because it is a D flip-flop. Okay. Now let us analyze the second stage where D will change its state from 0 to 1. But still the clock is in the I condition. Okay, when the clock is during clock is high, when the D changes, how does the output change? Let us understand. Okay, in this case D is 1. This input is initially, let us assume both are 1 1. Okay, this input is 1. Okay, and then this output will be should be 0. This input is 0, which will force the R to remain at 1. No problem. So when clock pulse is 1 and this, okay, this input is yes, hold on a second. Sir is calling. Okay, just a second. Really? Okay. Okay, yes, call disconnected. I'll call later. Okay, fine. Okay, yes, okay. Here it is. Okay, let's observe this. Initially, let us say S is 1, for example, to start with. Okay, so this is sorry. This is 1. This is 1. What is the condition of the this output of the NAND gate 4? It is 0. It is 0. Okay, 0 and 1 will force the output of the first NAND gate to go to 1. This input is now 1 because for the second NAND gate, both the inputs are 1, 1. S is forced to go from 1 to 0. Okay, S will change the state from 1 to 0. Okay, so now because of this, what is the condition of S and R? It is now 0 and 1. Okay, 0 and 1. Okay, okay. For a SR latch, if S is 0, what should be Q? Q should be set to 1. Q should be set to 1. Okay. So what we understand here is, of course, Q is changing, no doubt. But now when clock pulse is 1, okay. Now let us compare these two circuits now. Okay. Just a second. Satish, ಹೇಳಿ. ಹೌದು ಕ್ಲಾಸಲ್ಲಿದೆ. ಹಾಂ, ಲೆಸನ್ ಪ್ಲಾನ್ ಬೇಕಾ ಲ್ಯಾಬ್ದು? ಇದಕ್ಕೆ ಕಳಿಸ್ತೀನಿ, ಕಳಿಸ್ಕೊಡ್ತೀನಿ. Oh, okay, fine, okay. So let us compare these two circuits. So what we understand here is, when clock pulse is 1, okay, here it is, okay. When the clock pulse is 1, okay, okay, let us understand at this point. Initially, this is something like this. Initially, clock pulse was 0 in this first case, okay, and it rises to 1. When it rises to 1, when clock pulse was 0, 0, D was 0. When D was 0, Q was equal to 0. Okay. Now D changed to 1, but Q did not change to 1. Why? Because clock pulse was still 0. Now, when the clock pulse changes the state from 0 to 1, the output should also change, obviously, because there is a transition. That means there is a transition. During the edge of the clock pulse, what happens is that clock pulse is 1, okay, because of which Q changes the state from 0 to 1, okay, when D is set to 1. When D is set to 1, okay, fine. So this is what we observe now, okay. So thereby, this circuits is not that we are discussing this circuit independently. So this is in sequence, okay. So this is the first stage, this is the second stage, and this is the third stage, and this is the fourth stage. Something else, okay. Yeah. So in this case, when the clock pulse is 1, what we find is initially S and R was 1, 1, but it changes the state to 1, 0. Okay. So when S is 1, Q should be equal to 0. That means D is 0, and hence Q is also equal to 0. Okay. Now, because the clock pulse has changed from 0 to 1, 0 to 1, okay, when D is set to 1, what happens is, after some settling time, this is what is called as a settling time. Okay, that means after some short duration of time called as a settling time, output will change the state. When the clock pulse, see, clock pulse has changed, the output Q should have changed exactly at equal to this edge, as exactly at this point where the clock pulse change goes from 0 to 1. But practically it does not happen. Why? Because so many gates, each gate has a delay, and then the output takes some time to change. Okay, so thereby when D goes from 0 to 1, S and R changes the state from 1, 0 to 0, 1, 1, 0 to 0, 1. After some settling time, this will force the Q to change to 1. This will force the Q to change to 1. Okay, fine. Now let us analyze like this. Okay. Now in this condition, let us say if D is equal to 0, what happens? Let us say, okay, D is equal to 0. Okay. If D is equal to 0, this is 0. Okay. That means this is 1. This is 1, and then this is 1. Initially, let us take S and R as 1, 1. Okay. That's our initial condition. Okay. Somebody is on the line.
Excuse me, sir.
Yes.
Sir, Rajput is waiting outside the class.
I think, okay. You ask him to join me because I was in the, I was outside. If I'm outside this browser, it will not admit students automatically. So to admit, I have to come back to this web page.
He is in, sir.
Easy, nah? Fine, good. Okay, here we go. Let's continue. Okay, so yeah, here it is. S and R are set initially 1. Let us say, okay. So D was set to 1. After some settling time, Q becomes equal to 1. Now let us change D to 0. Let us see what happens. D 0, output of NAND gate 4 is 1. Okay, and because of this, input of third NAND gate is 1. Clock pulse is 1. Initially, sorry, initially S is 1. When S is 1, this is also equal to 1. This will force the R to change to 0. R becomes equal to 0. Okay, fine. Okay, R is equal to 0. This output of the fourth NAND gate is 0, is applied as an input to the first NAND gate. Output of the first NAND gate is 1. That is applied as an input to the, this, what do you call now? Second NAND gate. Okay, other input is a clock pulse which is equal to 1. Output of, yes, I know this, observe this. Output of the, the second NAND gate goes to 0. Output of the second NAND gate goes to 0. At this point, what we observe is both S and R is 0 0. Okay, for a NAND, SR latch with NAND gates, 0 0 is an invalid condition. But what does the flip flop does is, because of the feedback, it will automatically change. How does it changes? This S is now applied as input to the third NAND gate. So this third NAND gate becomes 0. When this third NAND gate, one of the input is 0, R will automatically change to 1. R will automatically changes its state to 1. Okay, fine. R is 1. When R is 1, let us say how the other gates changes. Okay, so this is 1. This will not make much of it will not make any difference for the output of the fourth NAND gate, because it remains 1. So 1 is now it was 1 alwa. Okay. Yes, did I? Oh, sorry. Oh, I made a mistake. Sorry. This was 0 actually. Okay, initially let us take 1 1. So now D is set to 0. I forgot that. Okay, D is 0. D input is 0. This is set to 1. When this is 1, input of the first NAND gate is 1. Okay, this is also 1. Because of this, output of the first NAND gate goes to 0 0. Okay, so this input is 0, which will make sure that S remains at 1. Okay, so S is one of the input for the third NAND gate. Clock pulse is 1, and this is also 1. There is, this, what do you call, um, this output of the fourth NAND gate is 1. This is 1. R transitions to 0. R transitions to 0. Okay, and because of this R transition to 0, so this input is 0. This will force output of the fourth NAND gate to remain at 1. No problem. Okay, so what we find is S and R changes the state from 1 1 to 1 0. 1 1 to 1 0. Okay, so when it is 1 1 1 1 to 1 0, what will happen is the Q has to change, because Q will change from Q will change from 0 to 1. It will change the state from 0 to 1, because the S and R has changed. Okay, so thereby, now what we understand here is, when the clock pulse, the summary of this discussion is, when the clock pulse goes from 0 to 1, this is the clock pulse. Okay, 0 to 1, as long as it remains in 0, let us say if D is equal to 0, then Q is equal to 0. Okay, and even now, during this duration, even if D is changed to 1, the Q continues to remain 0. When the clock pulse goes from 0 to 1, and when the D changes the state from, let us say initially 0 to 1, then Q will change the state from 1 to 0. It will change the state from 1 to 0 after some time, called as a settling time. Okay, now because of the clock pulse, when clock pulse changes, in this case, when the clock pulse is 1, then the, let us say clock pulse, so not clock pulse, sorry, when the D input changes, for example, from 1 to 0, 1 to 0, then Q will change the state. Q will change the state after some settling time. Okay, after some settling time, it will change the state to D0. Output remains 0. Output will be 0. Okay, fine. Now what we have to understand is, now the question is how long it's going to change, how long it's going to change. Okay, for example, if we take a clock pulse as, let us say time duration is 10 microsecond. Clock pulse, time duration is, for example, in our ADC laboratory, we have a 2 megahertz clock pulse. 2 megahertz clock pulse. Okay, so what is the time duration is? Time duration of one period of the clock pulse. Time duration is 0.5 milliseconds. Is it correct? 0.5 milliseconds. Okay. Okay. So total time period is, am I right, by the way? Oh, yeah, 0.5 milliseconds. Correct. 0.5 milliseconds. Out of 0.5 millisecond, on period is only 0.25 milliseconds. Point to half of that, 0.25 milliseconds. Off period is half of that. That is another 0.25 milliseconds. Okay, 0.025, sorry, more, 0.25, correct, 0.25 milliseconds. Okay, so thereby this duration is very small. In this duration, the number of times the D input changes is very less. Especially the circuit is will change the state when the clock pulse will go from 0 to 1. As long as it is 0, no matter number of times the input changes, output will take one state. For example, if D is 0, Q is set to 0 after some settling time. After that, even when the D changes, Q will not change. Q will not change. Q remains 0. Okay, so that's why it's called as a edge triggered flip flop. Okay, so it will change the state. The circuit is sensitive only during the edge of a clock pulse. Again, the same point is, edge depends on whether it's a positive clock pulse or a negative clock pulse. Based on that, whether it because see, for the same circuit, if it is a negative pulse, if it is a negative pulse, then falling edge comes first. Okay, clock pulse is initially 1, then 0. Okay, when the falling edge comes first, this discussion will be different. For example, initially we start with 1. Okay, clock pulse 1, then we change the clock pulse to 0. Then we change the clock pulse to 0. Okay, so accordingly the output will change. That's why we have to be particular about clock pulse, whether it is a negative pulse or it is a positive clock pulse. So based on that, the circuit operation is also going to change. That's okay. So this is what is called as a edge triggered deflow. In most of the cases where there is a possibility of noises in the circuit, edge triggered flip flops are preferred over what is known as level triggered flip flops. Level triggered flip flops. Okay. Okay, so here we go. Symbolic and symbols, I think we discussed. Okay, I think in the Yarbrough textbook we discussed SR flip flop. This indicates a clock pulse. In the absence of this, it is nothing but a latch. It is nothing but a asynchronous memory element called as a latch. This is JK flip flop, JK flip flop, and this is positive D flip flop with a positive clock pulse because there is no bubble, and this is a toggle flip flop, toggling flip flop or toggle flip flop. Okay, whatever you can call it as, toggle flip flop. Okay, in most of the logic circuits, as we discussed in the class, D flip flop is used than any of the JK flip flop or a T flip flop. SR flip flop is the basic for all these three types of flip flops. Okay, yeah, here we go. Yes. Okay, so next is the flip flop. Using flip flop, we can design the circuit. We don't have this discussion anyway. We can implement a Boolean expression using flip flops, just like we discussed for a multiplexers, decoders. Okay, similarly, we can do it for a what is called as using flip flops. I think I have one more topic to discuss, and then we'll jump to the registers. I think this timing diagram we discussed. That is triggered flip flops. Okay. Yes, it is also in this way. It's also specified. In this Yarbrough, it is specified like this. Okay. This example. Let us quickly see this example. What is on the line? Yeah, here it is. Okay. Yes, in this in this textbook it is shown like this. So let us say clock is 0, this is 0, and this is 1. Okay, that means it is still 0, and this has changed the state to 1. What should be the output? Output is 0. Okay, output is 0. Now when the clock is set to 1, okay, so this input becomes let us write it again. This is 1. Okay, that means it has gone from 0 to 1, and this side it will change the state from 1 to 0. Okay, 1 to 0. What should be the output? Means output should be 0. Output should be 0. Now guys, observe this. Now when the input okay, this is because both are complement of each other at some instant of time. Okay, so what is the point here? Clock edge. Output is clock edge. What is the clock edge? In this duration, if you see, as we discussed in the last class, actually, this clock edge. Okay, because of the delay in this inverter, what happens is that for a short duration of time, okay, both are logical. If we zoom in and if we write it clearly, it should be something like this. It should be something like this. Short duration of time, both are at logic 1. This is also logic 1, this is also logic 1. Output becomes set to 1, output is equal to 1. Otherwise, if the circuit is not sensitive to these edges, output will never be equal to 1. Why? Because if the clock is 1, other end is 0. If clock is 0, other end is 1. AND gate output will never become equal to 1 if the circuit is not sensitive to edge. Okay, if the circuit is sensitive to edge, output is set to 1 only for a short duration. Okay, if you write the output for this waveform, output should be like this. Output should be 1 only for a short duration, only for a short duration. Otherwise, output should be 0. Okay, so this is q, output q. Okay, so that's why it is called as a edge detector. This is how it happens. Okay, this is shown with a clock pulse, output of the inverter clock. So in this duration, short duration, we find that both are equal to 1. For the shortest duration, the output of the AND gate is 1. So this gives the what you call edge. Okay, edge in the sense, it gives a square pulse. Imagine that, guys, observe this. What is this edge detector is? Let us say, if we can modify the delay of this inverter delay, let us say we increase the delay. Okay, so when we increase the delay, this is let me write here. Okay, let me write here. Okay, so let us say this is the clock pulse. This is the basic clock pulse. We are increasing the delay of this this what is called inverter, for example. Okay, what happens is that because of the delay, initially the when the clock pulse was 0, what was the output of the inverter? It is logic high. Okay, ideally it should have been like this, theoretically, but practically what is happening is, because of the delay in the inverter, the output is like this. Output of the inverter is like this. For this duration, output of the AND gate is set to 1. Output of the AND gate is set to 1. That means we are generating a edge detector circuit where the duration of the output of the AND gate indicates the delay of the inverter. More the delay, larger is the pulse width of the output of the AND gate. Ideally it should have been 0. Practically, output of the AND gate should never become equal to 1. But because of the delay in the inverter circuit, here it is. Okay. So using this concept, edge triggered flip flops can be implemented. That's what we saw. We discussed. So we have two types. As we discussed, we have multiple types of edge triggered flip flop. For example, positive edge triggered flip flops. Okay. Similarly, we have negative edge triggered flip flops. I think here we can observe. Let me check. The clock pulse B is set to 1. Let us not go into that. This is a negative edge triggered, you know, JK flip flop. Timing diagram, I'll check, in case D is 1. Just hold on a second. In case clock edge is 1, clock edge, where it is, clock edge is this one. When this is 1, output depends on the J and K. Output depends on J and K. If J is 0, 1, 0, okay, let's observe this. Let us discuss positive quickly, just to understand. How the circuit is. Okay, clock edge is very short duration. That's what we understood now. Okay, clock edge duration is very small. Should be ideally 0 anyway. Okay, D is 1. When D is 1, at the same time, Q should have been equal to 1. But if you observe this circuit diagram, quickly understand. Observe this circuit diagram, guys. Initial stage is a edge detector. This is basically an edge detector circuit. Clock pulse is not directly being applied. It is applied through no edge detector circuit. Okay. So what is output of edge detector circuit? It's just a small duration clock pulse, very small duration pulse. Okay. So this is one, 2 and 4 inputs are one only for a short duration. Okay. Otherwise, it depends on the D input. For example, it is a D is 0. When D is 0, okay, output of the NAND gate S dash should be 1, and it is the D is complemented using this inverter, it becomes 1. So 1 and 1, R dash should be 0. Okay, so for a when the S dash is 1, R dash is 0, what should be Q? So 1, 1 is complemented 0. Okay, so it depends on the other input, set and reset input. Actually we have not discussed set and reset. Let us say both 1 0, for example, set and reset. Just a second. Set and reset, initially it is taken as it is not shown here. So hold on a second. Set and reset input. Any specific example is given for set and reset? Any initial condition? Hold on a second. Okay, okay, no problem. Set is, I'll tell you why is this set and reset. Let us take set as 1 and reset as 0. Reset input is somewhere here, 0 0 1. It is OR gate, so this output becomes 1. This input becomes 1 1 1 1. 1, it output is 0, so Q is 0. Guys, I'll explain this set and reset significance. Okay, in the flip flop we have a additional inputs called as a preset and clear. There is nothing but set and reset input. I'll tell you what is that. I'll tell you. Okay, so Q should be equal to 0, Q bar is equal to 1, Q bar is equal to 1. Okay, when S dash is 1 and when R dash is 0, Q is 0, Q dash is 1. Okay, fine. So this we understand, this concept we understand using this timing diagram. Okay, so thereby what should have been the initial cases? Ideally, when D is set to 1, Q should have been set to 1. Okay, but it does not happen like that, because S dash is 1 and R dash is 1. When both are 1 1, it is a no change condition. Q remains 0. Okay, when S dash becomes 0, when S dash, just look at this arrow indicates how the transition happens. When the clock pulse changes, output of the this is very important. Observe this. Though clock pulse has become 0 somewhere in this instance. Okay, let me try to zoom in, so that we can observe this edge. This edge is very important. Okay, here it is. I think this is too much of it. Okay, this should be okay. Yes, because observe the timing is very important. The clock pulse changes at this instance. Output of the inverter will not change immediately, after some delay. Okay, after some delay, when the clock goes from 0 to 1, output of the inverter will go from 1 to 0. Okay, clock edge is a small duration, only of this duration. Okay, this duration will affect the output. If D is set to 1, S dash is reset to 0. It goes from 1 to 0, 1 to 0, and R dash remains 1. Because the S dash is 0 and R is 1, Q is set to 1. Q is set to 1. Okay. Observe the duration, guys. This duration is because of the delay in the gates. Now, next observation in this timing diagram is that when clock edge becomes 0, okay, the S dash will go from 0 to 1. Okay, and R dash remains 1. So for a NAND SR latch, when the inputs are 1 1, output is not change. Output does not change. Okay, so even when look at this example. Okay, D is changing. Okay, so when when clock edge is positive, D is 1, Q is set to 1. Observe this. In this duration, I'm talking about this duration. D is set to 1. D is set to 1. Here, observe this. During this duration, D goes to 0. If D goes to 0, what should have been Q? In this instance, Q should have been equal to 0. It will never go to 0. Why? Because the clock edge is still 0. The clock edge was 1 only for a small duration. Later it was 0. Because it is 0 and the circuit is sensitive to edge of a clock pulse, though the D input changes to 0, Q will never go to 0. Q will change its state only when the clock edge pulse comes into picture. Only when the clock edge pulse is generated. If clock edge is 0, even when the D input changes, output will never change. Observe this. In this short duration, D is set to 1. This is D is 1. Still Q is 0. For the entire duration, Q is 0. Why? Because short duration D is 1, Q is 0, and when the clock pulse comes, when the clock edge comes, D is 0. Because of this, it makes sure that Q continue to remain 0. Q continue to remain 0. Okay, so this in this example, what we understand is circuit is made sensitive to edge of a clock pulse, thereby even when the D input randomly changes because of some disturbance in the circuit, output will not change until and unless edge of a clock pulse appears in the circuit. Is that okay, guys? It's very simple, This is significance of the edge triggered clock pulses. Okay, let's I'll discuss that. No, this preset and clear. There is set and reset input. What we saw here. Let us understand that, because in the practical laboratory, I mean in ADC laboratory, we have this preset and clear inputs. Let us, if I get one IC, I'll discuss that quickly. This is IC diagram. Okay, flip flop clock triggering preset and clear. I'm looking for one IC with preset and clear. I'll explain that also, because in the laboratory you have, and in the laboratory we have, and we don't discuss in the theory. That will not help, because the discussion will be inconclusive. Okay, catching ones and zeros. Okay, catching ones and zeros. Okay, master slave JK flip flop. Timing specification, this we discussed. Raise time and fall time, hold time. Okay, delay, this is what I was talking about, delay of the gates. Yes, where is the preset and clear of, okay, see, flip flop setup and hold time, setup time, hold time, and the delay time. Okay, um okay, guys, this is what actually then I was discussing. So it takes some time for the flip flop to set up, and it takes some time to hold. See, hold setup time means uh, when the input changes, output time taken for the output to change. Hold time means minimum duration for which the input should be one. Okay, for example, clock changes the state D. If D input, for example, this is D, this is clock. When the D changes its state only for a short duration, then it's of no use. D should be high or low for sufficient duration, called as a hold time, so that output changes. If D changes only for a short duration, then it less than the hold time, it will not affect the output. So that's the basic difference between setup time and a hold time. Hold time, correct. Okay, it is the same data input key output. Okay, propagation delay, fine. Flip flop meta stability. Okay, okay, it's fine. Okay, here it is. Let me check here when we get a IC with preset and clear. I'll discuss that also as a part of flip flops, so that okay. Let's quickly, let me open in the browser. I'll show you that preset and clear diagram, so that preset and clear is somewhere here. Yeah, here it is. Here it is. Preset and clear. Yes, here it is. But it is called as SD, and okay, SD is also okay. Set time and okay, okay. But I want that particularly preset and clear, so that in the laboratory we use that word, preset and okay. Let me search, preset and clear. I'll explain this. Preset and clear. Oh yes, here it is. Okay, yes, we have two diagrams. Okay, we'll discuss. Okay, now this should be okay. I discuss both the circuit breaks, so that we understand the difference. Why this came, I wanted that image. Where is the image? Where is the image? Hold on. Let me open in. Okay, open image in new tab. Okay, okay. This, can you see this, guys? I mean, I think this is slightly blurred. No, blurred image. Okay. Yes. In this case, what kind of flip flop it is, guys? Basically, it is a JK flip flop. Okay. In the JK flip flop, inputs are J and K. J corresponds to set, K corresponds to reset of the SR flip flop. We have a clock. Let's observe this clock pulse. What kind of clock pulse is this? Negative clock pulse. Negative clock pulse means when it is low, let's observe this truth table, function table. When the this down arrow in the clock indication, if it is a down arrow, that means it is a falling edge of a clock pulse. Okay, the circuit triggers during the positive edge of a clock pulse. That means it is a negative pulse, negative clock pulse. Okay, fine. Okay, what is this preset and clear? Let us concentrate on preset and clear. Okay, now, okay. Now, initially, let us say there is, in the absence of preset and clear, what should have happened? Depending on J and K. Okay, if J is 0, 0, output should not change. If J is 0, 1, q becomes 0. If j is 1 and k is 0, of course q is set to 1, that means it is a set input. When both are 1 1, it is going to attain a state called as race around condition. Okay, fine. Now we have what is known as a master is sorry, preset and clear. These preset and clear inputs are used to set Q and Q bar to a particular state which is independent of the input J and K. Okay, let's say I want to store 1. 1 means Q should be set to 1 irrespective of J and K, or I want to set Q to 0 irrespective of the condition input J and K. Then we go for preset and clear. How does the preset and clear works? Look at this, this diagram, guys. This truth table, it is split into function table, two tables, one with preset and clear 1 1. When the preset and clears are 1 1, it will not affect the output. Okay, but when the preset and clear changes the state, it will affect the output. How does it affect? When both are, what kind of input it is, by the way, guys? Preset and clear, they are active low inputs. Active low input means when it is 1, it will not have any effect. When it is 0, it is as an effect. Okay, when both preset and clears are 1 1, output q depends only on the input j and k and the clock pulse. Whereas if preset is set to 1 and clear is 0, this first we have to understand that 1 does not has any effect. Okay, if this as a what does the name suggest, by the way? Preset, pre. Initially set q to 1. Preset means pre. Initial condition should be 1. Clear means q should be 0. Q should be 0. Okay, so thereby when preset is 1, that means it does not has any effect, whereas clear is 0. Clear means clear the output to 0, and hence output is set to 0. Okay, guys, observe the names also. Asynchronous clear, it is called as asynchronous clear because output is not dependent on clock pulse. Output is independent of clock pulse. Not only that, output is independent of the input of the flip flop. Okay, when the inputs are 1 0. When the preset and clear is 0 and 1, that means preset is 0 and clear is 1. 1 does not has any effect. Preset is 0, that means output should be set to 1. One output is q is set to 1. This is called as a asynchronous preset. Whereas in the first part of the table, it's called as a synchronous. Whereas in the second part, it is called as asynchronous because it is independent of the clock pulse. When both are 0 0, when preset and clear are both are 0 0, output is invalid because output cannot take both 0 and 1 condition, which is invalid. Okay, so thereby in flip flops with preset and clear input, we have to make sure that either it is set to 1 1 when it depends only on the input and the clock pulse. Okay, or if you want to set output to 1, then preset should be 0. If you want output to be set to 0, then clear should be 0, and both should not be 0 0 at the same time. Okay, fine. This is the IC diagram. I'll show you the the circuit diagram. 2 more minutes, guys, just 2 more minutes. I'll show you the way this came. Okay, here it is. Okay, this diagram JK flip flop. I wanted this. Okay, yeah, very good. This is better. Okay, guys, look at this. This preset and clear are nothing but the what is applied to the IC. IC we had that preset input PR, and it is called as a clear input. Okay, CLR. Okay, fine. Here we go. Okay, is somebody on the line? I don't know. Here it is. Okay, anyway, yeah. Now observe this. How it's going to affect in the circuit. When both are 1 1, let's observe this. 1 1 is applied as an input to this NAND gates. This is first NAND gate, second, let us say third and fourth. Third and fourth NAND gate, when preset and clear inputs are 1 1, output of the third and fourth NAND gate depends on the other inputs. Correct? Because one is not a dominating input in a NAND gate. Whereas now, if preset is 0, for example, preset is 0 and clear is 1. So clear input is 1. The fourth NAND gate output depends on the other inputs. Whereas for the third NAND gate, since preset is 0, irrespective of any other input, that is S input or JK input or enable or clock input or clear input, okay, output Q is set to 1. Output Q is fixed at 1. It is asynchronous condition because it does not depend on the clock pulse, and hence it's called as a preset condition. That is irrespective of any other input condition or previous output condition, output is set to 1 preset. Okay, what about clear, guys? In the clear, preset is 1, clear is 0. Okay, this is the third NAND gate, this is the fourth NAND gate. So clear input is 0 now, preset is 1, output of the third NAND gate depends on the other two inputs, whereas output of the fourth NAND gate is set to 1. Okay, so because this is set to 1, okay, and this is 1, and output of the that first NAND gate, if either 0, if it is 0, output is set to 1, if it is 1, output is set to 0. But since it's a flip flop, if q bar is 1, q should be set to 0, because it's a complement of each other. Okay, so thereby what we understand is, depending on, okay, what happens if both inputs are 1 1, both preset and clear inputs are 1 1, both are 1 1, this will force q and q bar to be set to 1, q and q bar to be set to, not 1, sorry, q and q bar to be set to 0, which is a invalid condition, so thereby, very simple, if you want to operate the flip flop as a synchronous element, preset and clear should be 1 1. If you want to set q to 1, preset should be 0. If you want to set q to 0 irrespective of the input condition, clear should be equal to 0. Okay, and both are 1 1, which is corresponds to invalid condition. Yes, okay guys, fine. I think it is a time up. Yes, here it is. Okay, it's fine. Thank you. It's already time. See you in the next class. Take care. Bye. Bye.
Thank you, sir.
Okay.
Thank you,
Bye.
sir.
Bye. Bye. Bye.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Bye. Bye. Take care. Bye. Bye.
Bye, sir.
Bye, sir.
Thank you, sir.